Okay, today we're going to talk about Matt Dunning and his umbrella. You can tell this is Matt Dunning because look at that flat brim on that hat. And little did you know, Matt has his favorite Yankee umbrella. And there's a statement that is always true. And that statement is, if it is raining, Matt opens his umbrella. So what'll happen is Matt will look outside and see what's going on. Let's look outside. Uh-oh, Matt, it's raining outside. So what is Matt going to do? That's right, Matt's going to open up his Yankee umbrella to keep himself dry. So this statement is always true. If it is raining, Matt opens his umbrella. What about some other statements based on that information that we have there? We're going to take a look at two others on this next page. And we're going to look at the converse of this statement. And the converse of a statement says, it just flips the if and the then. It says, if Matt opens his umbrella, then it is raining. Well, that's not necessarily true. Maybe it's a hot sunny day, and Matt's just very concerned about his delicate skin getting sunburned there. So he may open his umbrella. He's still allowed to open it if it's not raining, but if it is raining, then he definitely opens his umbrella. Let's take a look at the other condition. So the converse is not always true. Let's take a look at the inverse, where we just negate the beginning and the ending. If it is not raining, Matt does not open his umbrella. Well, our statement right here says that's not necessarily the case. Matt, hey, come back here, Matt. There we go. If the sun was out, he opened his umbrella. So if it is not raining, Matt does not open his umbrella is not necessarily a true statement as well. These are not necessarily true. There's only one statement that is always true. If you're given an original truth statement, like P then Q, the converse and the inverse may or may not be true. You just don't know. But if you combine the two, if you negate everything and flip it, if Q, then not P, that is known as the contrapositive. And that statement, the contrapositive, is always true. Always true. So in this case, I'm going to flip both. This statement, if Matt does not open his umbrella, it is not raining, is always, always, always true. Meaning, we know when Matt looks outside, he sees it raining, he's going to open his umbrella. Well, if he didn't open his umbrella, then we know it's definitely not raining outside. The contrapositive, the negation and the flip of the P's and the Q's is always, always, always true. Now, what does this have anything to do with what we're working on? We've got this big fancy phrase. Differentiability implies continuity. It just means, in the long and short things, that if something is differentiable, then it is continuous. I'm going to write that statement down. If a function is differentiable at x equals c, then it is continuous at x equals c. If we already know something is differentiable, we can automatically conclude that it is continuous. Sometimes we can't see the original function. Sometimes we can just see the derivatives, and if we know it's differentiable at that point, then it's definitely, the original function itself is definitely continuous. But because this is true, the contrapositive is also true. So I'm going to flip and negate both sides. I would then say if f of x is not, I'm going to grab this one, continuous, at x equals c, then it is not, I'm going to grab this part, differentiable. Ooh, long word to spell. At x equals c. Meaning, it's not continuous, you already know you're not going to be able to find a derivative. If it is differentiable, then you already know it's continuous. Let me just show you a quick example of what I mean. For time-related purposes, I am removing arrowheads, and they will not count as Cuba dollars in this video. Let's take a look to see if things are going to be differentiable or continuous at x equals c. So we take a look at the first one, and I see a cusp right here. I know this one will be continuous, but it will not be differentiable. C, not diff. How about the next one? I already see it is not continuous at C. If I know it's not continuous, guess what? You already know that it's not differentiable. Let's take a look at the third one here. Oh, it's not continuous, so both things are not true. Not differentiable. So essentially, if you already know something's continuous, you know the next step. It's not differentiable. But if you know something is differentiable, then you already know it's continuous. Take a look at this one. Oh, look at C. It's a smooth curve. Therefore, I know it is continuous. And it's not a cusp, so it is also differentiable at that point. Where this will lead us to tomorrow is to take a look at piecewise functions. With a piecewise function, we may have one piece coming from one function and another piece coming from another function, and they may meet at a point. If these two parts of the function meet, I would already know this function is not differentiable. Why not? You're right, because there is a cusp. What we would try to do is try to find a way to take the blue part and add it in there so we get a smooth curve. And if we can make it smooth, then this new function, this piecewise function, f of x, which is made up of two pieces, will then be differentiable. How are we going to do that? Well, we're going to make the derivatives equal to each other, but we will look at that tomorrow. I hope this video has been helpful. Please feel free to watch again to be ready for tomorrow's lesson.